Okay, good morning. Today we have a very nice session. Is because it's unsteady. We have transients, we have animations, we have evolution of a given profile or field distribution in time, and this is actually very nice to implement. And something that is surprising is that it's gonna be very simple. So we have already done the hardest part, in my opinion, which is discretizing the space that can be eventually, as we already did, given by a non-Cartesian domain. So something that is not like regular. And we spend some time deriving finite differences, finite volumes. Right now, everything is done and we can go on and discretize time. So this is just a reminder. We already did this. We will do this in the final session. Next session is also very interesting. We will consider, or we will actually understand how to solve a linear system of equations. So as already said, we already fulfill this task. Now we will fulfill this other task. Something that is important to remember is that this is not the same as this one. I have seen some courses, some lectures when this is somehow mixed in the same numerical scheme, and that can be actually very confusing. So I want you to first do think in this way of splitting what is space and what is time. Okay, now that we have a space, and this space is just given by the matrix A, we already have this computational matrix, we will just now go on time. And a motivation is, for example, to understand convergence in time and which are the conditions to fulfill these convergent numerical schemes. If our problem, our case of interest is inherently steady, we should be able to reach this steadiness after a transient. And sometimes how fast you arrive to this steady state is important in terms of how this transient simulation modeling is important. Sometimes it's not. Let's assume that this is important. We need to know the evolution as time elapses. Now we have maybe several parameters to take into account. One that is super important is the time step. And let's assume we just consider a time step that is 1.5 milliseconds. We have everything done and we just run our simulation, and we see that everything is going fine, and suddenly everything goes wrong. At a given moment in the simulation, you have a numerical instability that makes everything crash. Okay, now we do our study. We take we consider non-dimensional numbers that are pretty important for convergence, which are the Courant number, for example, or the diffusion number. And we realize that we need to have a time step that is 1 millisecond or smaller. Then we just go and run our simulation, and the initial part is very similar to the one we had just before, but happily this time we reach a steady state and we don't have any numerical instability. And this is because we understood which conditions we needed to have or needed to fulfill to assure convergence. We can have even a more interesting example. The previous slide we were considering an explicit scheme. We will see that today. And under some conditions we will realize that this numerical scheme is conditionally unstable, so for some cases. Now if we go to an implicit scheme, in other words, you can have a backward Euler. Again, we will see that today. there you can see, you can make the mathematical derivation for the stability condition, and you will realize that this is unconditionally stable, which means that no matter which time step you use, your solution will not crash. And this will not crash doesn't mean it will go and will actually be very accurate when modeling the transient. This is a different thing. So you may think because your solution didn't explode, everything is right. Actually, it's not the case. Let's imagine we are just look at the first instance in the evolution of the temperature. So let's take a look. I will do play, left video. Did you see these oscillations at the beginning? So let me just replay it again. So these oscillations of the field at the beginning, they are there. So imagine you are working with a problem and you see that you have oscillations, and this can be dangerous for the system operation. And then you say, watch out, we have oscillations in the system. But then you question yourself, are they actually physical oscillations, or they are just coming because of the numerical scheme? And this kind of situations can happen actually with unconditionally stable. So your solution didn't explode. Actually, it eventually reached the correct steady state, but the transient was not correct. If you then set up your parameters in a correct way, you have the same problem, but the transient right now is correct because it does not oscillate. This is a much more realistic case. Okay, this is actually a diffusion problem. Therefore, these oscillations are weird. Let's say they shouldn't exist. But this is just to make you understand that unconditionally stable numerical schemes also have their own problems. Okay, so you have to watch out even in this kind of numerical schemes. In our case, it's gonna be the implicit scheme. Okay, so let's start with this equation. We can already identify three terms. The first term is the unsteady term. The second term is a convective term, a convective flux. And the third one is a diffusion one. So this is the one we have focused so far. So the spatial discretization of this one. This term in this two-dimensional approach is already simplified. You could eventually also have the velocity in y direction, but we just keep it just in one velocity, so with just one component for simplicity. But it doesn't exclude that we could also include the convection in y. And then you can discretize this term depending on the problem of interest. You can have finite differences, finite volumes, also finite elements. We don't see finite elements in this course, but you could eventually also have this discretization. And also the convective term. This is just a way of notation of these operators. Okay. Another question is how to discretize this term. So we can use explicit schemes, implicit schemes, or something that is very classical as well, which are iterative schemes. If we go with explicit schemes, we get this expression. So we can interpret it. Imagine we are somehow here, n is the present, and we want to predict the future. Therefore, you discretize your operator in this way, like finite differences if you want, and then you just express the t of the operators in the convective and diffusion operators with the present temperature. So you can actually rearrange this equation as this one. and find out that you can actually advance in time just by making some matrix vector multiplications. So remember that for us, just to make it clear, these are actually matrices. So this is nothing but the A matrix we use most of the time. So you just do matrix vector multiplications and you are able to actually estimate the future state, so the future distribution of temperature. So let's focus now on the problem of our interest. Then we don't consider the convection, we will consider only diffusion, and then we just write our equation in here. So this is temperature, then the diffusion, and then we will have the corresponding source. We can have three kinds of boundary conditions. We can have Tp is equal to the surrounding temperature. We can have also, so this is Dirichlet. We can also have Neumann. So we have, sorry, this is a dot minus, so Tp is equal to the flux. Or we could also have Robin. So if you remember, okay, I forgot the normal vector, which is pretty important. Okay, so here is the normal. Okay, and we know that all this can be actually, so all this is enclosed or is written in terms of a computational matrix that we call A. So our system of equations is going to be like a semi-discretized system of equations that reads like this. Now the question is, what is S? And we can actually then remember what we have done so far. So far we have actually solved this equation, and we have written this in terms of okay, so now you're familiar with this vector called V. Now you just see the left hand side. We need to do is to multiply everything by a minus, so because we want to have minus this Laplacian, therefore we need we already have this, the first part, and the second part is actually a minus b, just to be consequent. Just to point out, I'm not considering lambda. It's like lambda is equal to 1, but you could without problem just add lambda in these equations, okay, and nothing actually changes, basically nothing. Now we interest ourselves on this, and we are using the explicit scheme, so it's like we are using finite differences for discretizing this temporal operator. So this is also known as forward Euler. So we have here t n plus 1 minus t n over delta t is equal to at minus b. And the important part in here is that you may wonder when this temperature is actually evaluated, is in the present or in the future. Actually, this is the critical thing, and this is why this is explicit, because we are actually just evaluating everything in the present to estimate to estimate the future. So this is going to be the present. Now if we reorganize this equation, we will obtain t n plus 1 equal tn. Then is gonna have, we have here plus delta t a t minus b, and that's all. So you see here that we just need to have the present to estimate the future, and we don't need to solve any linear system. So explicit schemes are actually very useful when you have very large matrices in terms of like millions of tens of millions of elements in your mesh, for example. Then imagine the size of the matrix is gonna be huge, this A matrix. Now invert, or let's say solve the corresponding linear system would be super expensive. Therefore, there are many codes, commercial codes and also scientific codes, that just do this kind of explicit scheme, maybe with some modifications, adding some steps. This is the so-called iterative schemes. But the basic idea is that they don't solve any linear system. They just advance in time based on the information you have at the present time. And therefore, things get easier. Let's say simpler in terms of computational efficiency. Now, there is also pros and cons, like always in engineering. So you have that in order to maintain the stability of these numerical schemes, you need to have most of the time very small time steps, like in here. So these are very small. Therefore, if you put a very large delta t, you may have your system of equations just blowing up. We will just discuss this in the next slide. So the method, the way I'm introducing this here is very nice, because you see that the matrix A is exactly the same, the one you have already computed, the one already you have derived, and already has inside the boundary conditions. So you don't have to worry about the boundary conditions, because this is already satisfied by this equation. Okay, now what we worry is to just compute the transient. What else? In addition to the boundary conditions, which are already enclosed, summarized in the matrix A, we need an initial condition, and this is just a distribution of temperature at time 0. So in this case, the first calculation is gonna be, this is gonna be time 0, and this is gonna be time 1. And the time 0 is something you have to give to the algorithm, and this is just an initial condition that makes sense. Now, under this method that I'm presenting you today, there is something that is very important, please do not forget, is how you impose initial conditions that make this system remain stable. In order to do that, you need to impose, if you want to have Dirichlet boundary conditions, you need to have the initial conditions already being satisfy the boundary conditions if they are Dirichlet. I just make an example. Let's imagine we have this domain, and we want to impose a Dirichlet boundary condition at the west, in here. So the initial condition, imagine the boundary condition is 100. 100 Celsius. So you just need to impose an initial condition that makes sense. Now imagine the surrounding here is gonna be 30 Celsius, and we have here Neumann, Robin, and Robin. So what we need is to impose an initial condition that satisfies this boundary condition, the Dirichlet one. The other ones doesn't matter. So you can have, for example, something like this. So in these nodes, you will impose 100. In the other nodes, you will impose 30, and then you just let the simulation evolve, and you realize that then you will have this temperature here being, or this heat being diffused until arriving to a given equilibrium point. You could also have all this domain equal to 100 hertz, and you will see that you will have at the beginning large amount of heat flux through this wall. Oh, through this wall you don't, because it's Neumann, but in these ones, and then you will have at the end a steady state. So in these two cases, the initial conditions were different. So the first one was 100 and then 30. The second possibility was everything 100, but the steady state is going to be the same. So the initial condition is different, but the final solution is going to be the same. That's why we have actually a linear system of equations. And again, what is important in here is that the initial condition is satisfying already the Dirichlet boundary. Okay, now you may wonder, fine, then tell me, what is this delta T? How large or how small can it be? For that, we'll go to the next slide. And then we ask ourselves how to compute this. And actually, this is not simple to do. There is this guy, maybe you already know him, he's called von Neumann. He did a very nice derivation for the stability of numerical schemes. And his analysis is actually recognized as von Neumann stability analysis of, in this case, the forward Euler scheme. But in order to carry out that analysis, there must be some assumptions that need to be fulfilled in order to have an analytical derivation of that. And the first one is that the system of equations used, you will have a convective flux, you will have a diffusive flux, but we will consider one-dimensional cases. Moreover, we will just consider finite differences as the numerical scheme to discretize the equation. And to finish, we will consider boundary conditions that are periodic. Periodicity means that everything that happens to the right happens to the left, so they are communicating. So they are actually like the same boundary condition. So under this approach, you have an equation like this. So this is the first thing, this is the same thing we saw just before. We discretize this. So this system by forward Euler, everything here is in the present. This is going to be the future state, so the future distribution of temperature. But now, since we are talking about finite differences, we can, and 1D, we can just have a very simple operator. In here we can have the diffusion operator. You already recognize the shape of it. This is east, west, P, east. This is just a centered scheme as well. So if you do that with this finite differences representation, then you can obtain the following non-dimensional numbers. So the first one is the so-called Courant number, and the second one is the diffusion number. So under the von Neumann analysis, you can see that in the section 411 of the manuscript. I will not talk about this in the lecture, but you can just go to the section and read it. I think it's pretty clear. It's possible to realize that you will have a stable numerical scheme as long as your Courant number is smaller than 1. So we can write it in this way. So x delta t over delta x, which is nu, has to be smaller than 1. That means that delta t has to be smaller than delta x over v over x. and this already sheds some light on the understanding of delta t. So you can already have two conclusions in here. The first one is, imagine you need to resolve, so to make a refinement of the mesh somewhere in your domain, just to be able to capture some physical phenomenon. Then you just decrease the size of delta x, so the cells they are going to be smaller. Automatically you have to think about the time step. You can say, okay, if I reduce the size of the mesh, I will need to reduce the time step as well. And this is actually, it can happen that the numerical instabilities always show up first at the smaller cells. This is one thing. Other interesting implication is that the velocity of propagation of information. So in this case, the velocity is actually the convective one. So if this is the system of interest, now if somehow you have a large velocity, then it means that you need to decrease the size of the time step. So you may be trying to simulate a system that exceeds a given velocity, convective velocity, and everything is working fine. And then you increase the convective velocity and your solver just blows up. It's because as you increase this velocity, you have to be aware that you have to satisfy also this relation in here. Okay, so we have to do now emphasis that this is a von Neumann analysis, which is actually derived from a very simple problem. So this is gonna be this problem, which is one-dimensional, will guide us to be able to control, in this case, the Courant number. Is also sometimes recognized as Courant-Friedrich number or the CFL condition. So this is actually related to the CFL condition. It gives us a hint. In this case, it tells us, watch out, this Courant number has to be smaller than 1. However, in real systems, let's say in real numerical problems, you have three-dimensional geometries. You have boundary conditions that are not actually given by periodicity. So you have Neumann, Robin, and you have something that cannot be just shrinked to such a simple formulation. Then you may think, yeah, so let's just do something similar to the von Neumann analysis, but now to our discretized method, let's say finite volumes instead of finite differences, and consider three-dimensional geometries, and consider maybe boundary conditions that are more complex than just periodic boundary conditions. Nobody, or I don't know of anyone that has succeeded doing that. It's actually maybe impossible, and also maybe a tedious exercise that is not general, because if you were able to carry out such an analysis, maybe you have an enormous equation that is actually important only for the system that you are studying, nothing else. It cannot be generalized. So what you can think about this CFL condition and the Courant number is that this method derived from the von Neumann analysis gives you a hint, but the real CFL condition instead of 1 can be, for example, 0.7, and this is not because you were able to have the formula giving you like this has to be smaller than 0.7. It's just trial and error. This is more like an empirical work. Then the idea is that you get a hint, which is 1, and then you just try several cases, several boundary conditions, certain geometries, and to be safe, in the safe side, you say, okay, I think the CFL has to be maybe not smaller than 1, but smaller than 0.7, just to have a margin for error. Now, if we carry out the same analysis with this equation with this system, then we find out that the diffusion number has to be smaller than 1/2, than 0.5. Again, this is a hint and a help that need to be somehow proved by doing some empirical work with the system of interest. So maybe delta is not going to be 0.5 but 0.4 or something like that. In the manuscript, I show a two-dimensional derivation for this diffusion number. So again, we are interested in this course most of the time in the diffusion part. So in this course, we will not care about the Courant number because we will not consider any convective fluxes in the equations. So this is like it doesn't exist for us, and we will just consider this with the diffusion number that for one-dimensional cases is suggested to be smaller than 0.5. But in the manuscript, with the help of Killian, so the other guy that helped developing this course, we have the equations. I will just write it down in here so that you can just see in the manuscript. Equation 4.39. So in this case, is the stability condition for when you have delta x not being equal to delta y, so you can have a delta x, delta y be different, and for again two-dimensional cases. So it's like a general expression, more general than the one shown here. This is the classical one. So the idea of today is that you will go evaluate the condition given by this diffusion number, by the 4.39, and then you will use it as a hint, as an idea of where to start your, let's say, numerical experimentation. So you just use the diffusion number that this equation gives you, then you evaluate the corresponding delta t, and maybe things keep exploding, then you just say, okay, maybe let's reduce it by 10%, and then you will end up finding a delta t that is satisfactory for your investigation. Okay, so far we have discussed only for Euler or means explicit schemes. Now we will go to implicit schemes. So we already saw that this scheme here is conditionally stable, which means that under certain conditions you may have an stable system. So in that case, before was summarized in terms of Courant and diffusion number. Now this system, if you actually carry out the same analysis, you will realize that is unconditionally stable. In that sense, at least theoretically, and at least for the case that von Neumann uses, which is these one-dimensional finite differences with periodic boundary conditions. For this case, you cannot have something that explodes if you have an implicit scheme. As already saw in the introduction, and you will also realize today, you can, when you use the implicit scheme, also recognized as backward Euler, you can use huge delta t's, very, very large delta t's. Anyway, after a certain threshold of delta t, you may have starting to have like unrealistic fluctuations, like numerical oscillations. Still, your system does not explode, but the transient that you are simulating is not physical. This was the video I showed you in the introduction. This is a very interesting thing. Okay, so let's go to implicit schemes. Okay, so we go back to our equation, and the idea is that we will use now, let me just put it in here, Tn plus 1 minus t and delta t. So far nothing changes. Then we'll have here at minus b. So for the explicit scheme, we were using here the present information, which means n. Now for the implicit schemes, which is backward Euler also, we will consider the future state. In that sense, we will have here n plus 1. And this is actually the fundamental difference. Now we will have to reorganize the equation and we will have at the left hand side the future states, at the right hand side the present ones. So let me just do this. We have Tn plus 1, then we will have here minus delta T A Tn plus 1, then we will have here Tn minus B. So in here we just make some factorization. Here remains the same. Okay, so this is going to be a matrix and this is going to be a vector. So we'll just put here a name to this. We will call this A star, and this is going to be B star, and that's all. So what does it mean? That we will need to solve for each time step a linear system of equations, A star T equal B star. Okay, here is n plus 1. So when you do this in your coding, then you just have to construct A and B at every time step to solve them for n plus 1, and then you just go to the next time step. You will realize that actually you can use very large delta t's. Okay, so you can actually play around with that and see until when you can go and how larger the delta t can be used if compared with the explicit scheme. We will talk now about another scheme called theta scheme. So we start exactly as before, Tn plus 1 minus Tn delta t Et plus minus b. Okay, now how we consider this t? And this is now when the theta scheme enters into the game, we will say that t is just somehow like a waiting between the present and the future. So it's like a somehow like a weighted sum. So we will just call a variable theta multiplied by Tn plus 1 plus theta minus 1. Let's say, sorry, 1 minus theta multiplied by Tn. What does it mean? It means that if theta is 0, we will recover the explicit scheme. If theta is 1, we will recover the implicit scheme, so the fully implicit, which is this Bauer-Euler. But you can have thetas in between. You can have 0.5, for example. So you have a theta equal to 0.5, then you have an average between Tn plus 1 and Tn. This method, so when theta is equal to 0.5, is called Crank-Nicolson. And is pretty popular. So you can continue. I will stop in here, so you can just do exactly the same thing we did before to derive the corresponding theta scheme. Okay, so this is part of the exercise, that's why I will just stop in here. So we have this classification of theta. I just said it in the previous slide. Now an interesting question is which one of these present a better order of accuracy. Now we are talking about accuracy in time. In the second class, if you remember, we were deriving finite differences scheme and we were talking about accuracy but of the spatial discretization. Now we are talking about accuracy of the time discretization. And in this case, we can actually, or you can demonstrate it also by doing Taylor expansions if you want, that the Crank-Nicolson is second order accurate. while this explicit and implicit are just first order accurate. So if you use theta, then just use 0.5 because this is the best compromise. We have seen so far then how do we discretize explicit, implicit, also we have this average one. Then let's talk about iterative schemes. Iterative schemes is like a recipes, if you want, that combine all what we have just seen before. So in order to have this clear, let's have an explanation. So if I show you this equation like this, you can think this is what? This is like an explicit scheme, no? Because we have present in both cases here, and this is the future. But instead of doing this, we can just split the task of predicting this future in two steps. One is going to be called the predictor, and the other one is the corrector one. If you look at this is actually the same as this one. But now instead of saying, yeah, I find the final estimation for the future of the temperature, I will say I found an estimation, yes, but it's not my final answer. I will do an additional step. And the additional step, you put it in here, what you just found in here. And if you look at this scheme, it resembles the Craig-Nicholson one. You see here, this is the present, this is the future, and this is half, and then you will have the actual future, so the final prediction. So you can see that even though we have used the Craig-Nicholson, we don't have to solve a linear system, and this is the main purpose of it. You can increase the order of accuracy of your time discretization, but you still are able to avoid solving a linear system. Then you have just matrix vector multiplications to evaluate the temperature at n+1. Numerical scheme as shown in here is called the Runge-Kutta 2, but it has some stability problems. So what you can find most of the time out there in scientific coding, also in commercial codes, is the Runge-Kutta 4, and this is the one. So this is the Runge-Kutta 4. The order of accuracy is 4, so it's very, very high order of accuracy, and still you don't have to solve any linear system, which is what we want. So just know that anyway we have this conditional stability problem, which means that we have to control, in our case, the diffusion number. If you have just large delta t's, thing will explode anyway. Okay, so what is this about? The first thing is that you will carry out again the forward Euler, but instead of going all the way to n+1, you just go to n+1/2. So basically here you just having half of the delta t because you just advance to n+1/2. So this is a prediction step. Then the correction step is basically a implicit scheme, or like a Bauer Euler, but remember that now we will use the information in here like as a guess to obtain a second step guess of n+1/2. Now we go here, and this one is actually a midpoint rule of integration in time. Okay, maybe some of you will be now lost, but let me then explain something that I consider very, very, very cool, very interesting. So here we will have our time, and this is gonna be temperature, and this is the evolution of temperature for some reason at a given point. And then we have the interval n and n+1. If we consider now our equation, so the one we have worked so far, we can see that this can be a given operator. Let's call it f. and then we will just want to integrate. So we'll just split this. We just say I want to integrate dt, and here I will integrate ft dt, and this is what we're doing. Okay, integrating this function in here to note tn and tn plus 1. Now we can approximate this. Okay, so here is actually f of t. So we can approximate it by the forward Euler. Forward Euler means that we will just consider this point and then we integrate in time, which means that we are actually integrating this surface until here. So this surface. So this is our approximation with forward Euler. Backward Euler is actually you consider the value in here and then you integrate and here, so this is going to be the integration. The trapezoidal rule in this case for the integration is nothing but the Crank-Nicolson, because the Crank-Nicolson is like a trapezoidal rule that needs the information. It's like an average between, sorry about this, between the future and present. So it's going to be like a trapezoidal rule like this, and this is the one, okay, we recognize as Crank-Nicolson. So you can also see that we can also use the midpoint rule in here. Okay, this is m plus 1 over 2, and then the midpoint rule it will give us, let's change the color, will give me this area. And this is what we are doing. We're seeing here. We have seen the first step is based on forward Euler, the second one is based on backward Euler, and the third one is based on the midpoint rule. And you can have more sophisticated time integration schemes, which, for example, the Simpsons rule. The Simpsons rule uses 3 points instead of 2. So for example, this one, oh god, let me just put in, is this one actually. So this one, and maybe one in the middle. So the integration is going to be very nice. It's going to follow almost the real path of the f of t. And this is what we do actually in the fourth step in the Runge-Kutta 4. So this step is actually given by the Simpsons rule, and we use the information of the previous steps to compute the temperature at the future. This is a very famous scheme, so this is worth you will implement it in the exercises. This is a complementary exercise, like optional, but I strongly suggest that you actually do it. In the scriptum you can find these steps for our case, so it's more explicitly explained, AT equal B, so this is going to be more clear in the scriptum. Okay, so today we'll have fun, a lot of fun, because it's going to be very simple. You will see you have the matrix A already. This was the hardest part. Now you have just to start playing around with different numerical schemes for time, and you also can play around with different initial conditions and also different shapes. I mean, we don't have to really limit ourselves to this system, but we can just have this one. I saw once, maybe 3 weeks ago, like a sinusoidal shape. It was like something like this, and see how the temperature evolves, maybe with Robin boundary conditions. So actually right now you can do pretty complex stuff, but still you see that things are actually not as hard as you maybe may have thought at the beginning before the course. Okay, and this is gonna give you much more tools for the execution of your projects. Okay, so this is the end of the video. Thank you very much. See you next time. Bye bye.